Dr. Ranjani Parthasarathi is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. We have been looking at some basic operational concepts and looked at instructions. We have looked at detail, we have looked at instructions in detail, we have looked at arithmetic, logic, data transfer, control instructions, and we have looked at different addressing modes. So, what we need to look at now is to understand how these instructions get encoded. So, before that, a quick review of the addressing modes. Just take a look at a few examples and see if you are able to recollect how these addressing modes work. So, we have the memory indirect addressing. So, add R1 comma say some address which is specified, let us say I have at here which is used to indicate, for instance, that this is a memory indirect addressing, and you specify the value R3 here. This should be register indirect addressing. So, we specify the value which is there in this the contents of this location R3, and the memory value of that is taken, and then we have the data taken from that memory location added to R1 and stored in R1. You have the auto increment instruction, so which is normally specified like this, add R1 comma R2 plus. So, R1 will take the value of R1 plus the memory value specified by R2, and then the R2 value will be added with some increment value D. So, auto decrement similarly, add R1 comma minus R2, you will first do R2 as R2 minus D, and then we will do this address calculation using the location which is specified in R2. Then we have the scaled addressing mode. So, let us say we have add R1 comma 100 of R2 and R3. So, here it will be given the value that we will be taking will be calculate the memory location by adding 100 with the contents of R2 and the value R3 scaled by a factor D. Okay. So, as we said, these instructions are useful when we are dealing with arrays. So, for instance, when I have a 2-dimensional array, the D size could be the size of the array if it was, say, for instance, organized in a row major order or whatever, and in that case number of rows. So, if I am looking at say the 10th element of the 11th row or so on. So, accordingly we can specify the value of D and use appropriate values in R2 and R3 in order to access that location. Okay. This is what we have looked at earlier. Now, the reason we need to again look at addressing modes is to understand how these addressing modes play a role in the encoding of instructions. So, what do we mean in terms of encoding instructions? We are now talking about how these instructions actually are represented, right. So, we know that an instruction will have an opcode and it will have the operands and so on. So, how many bits do I specify for each of these fields? So, these are decisions that need to be taken when you are looking at any instruction set architecture design. So, what we will look at therefore today is we will look at how this encoding gets done, and we will look at an example of we will look at some examples of some instruction set architectures to get a better understanding of how these concepts that we have looked at now are actually used. So, coming to our encoding of machine instructions, we know that assembly language program needs to be converted into machine instructions, right. So, what is it that needs to be specified? As I said, opcode has to be there, the type of operation to be performed, and the type of operands used may also be specified using some encoded binary pattern. Okay. So, let us say for instance, I am looking at a condition like this. I have a 32-bit word length for my instruction, let us say. So, suppose 32-bit word length is specified and you have 8-bit opcode, okay, which means, so if I have an 8-bit value specified for the opcode position and I have 16 registers in total and 3-bit addressing mode indicator. In this case, what would my instruction format look like? So, just let us just go through this again. My total word length is 32 bits. So, my instruction word length is 32 bits and I have 8 bits for the opcode. Now, given that I have 8 bits for the opcode, how many instructions can we have? If you have an 8-bit number, you can have 2 to the power of 8 different combinations, which means I can have 256, 2 power 8, 256 different instructions can be specified. Now, when I said there are 16 registers in total, so how many bits are required to represent each register? So, with 16 registers can be represented using 2, which means 16 registers is 2 power 4. So, with 4 bits you can represent each register. So, which means I need 4 bits to specify each register, and then I am using 3 bits as the addressing mode indicator. Now, remember we just talked about different addressing modes, and for every operand that is being accessed, you may have to specify what is the addressing mode that is used, because we specify R2 and we say R2 in brackets. Now, how do you actually specify this R2 in brackets or whatever to specify whether it is a direct addressing mode or an indirect addressing mode? So, this addressing mode will have to be encoded in the instruction, so that when you decode the instruction, the hardware will be able to find out what to do with it. You have to specify an addressing mode indicator. So, given that I have these different specifications, what will my instruction look like? So, you will see that if I have a one word instruction, this is what it will be able to represent it as. That is, I am using 8 bits for the opcode, right. So, first let us say I have a field of 8 bits which is given for the opcode, and then I have a source field and a destination field. Assume that I am using a 2 operand instruction format. Okay. So, source you can see is taking up 7 bits. Now, why do I need 7 bits here? Because I said there are 16 registers in total. So, we said 4 bits are required for the register and we are using 3 bits for the addressing mode. So, 4 plus 3, 7 bits are used for the source operand, and similarly 7 bits are used for the destination operand. Plus we have another 10 bits free. So, because we said 8 plus 7, 15 plus 7, 22 bits have been used. There are other 10 bits available in our 32 bit instruction, which could be used for storing some other information. So, this is how an instruction of this nature would have to be coded. So, when you are looking at an instruction, what we need to do therefore is to determine how the coding will be done. We have to look at the different instructions that may have to be supported, right, and you will have to look at what are the operands that need to be specified for each of these. You have to look at what are the different addressing modes that will be specified for each of these operands, and make sure that all this information is represented within the instruction that is given to you. So, arriving at a particular format in which these things can be represented is an interesting task that needs to be done for this instruction encoding. Now, what are the challenges here? The challenges are that if you have too many different addressing modes and too many different formats in which the information can be specified, decoding it can become very complex. So, we normally try to group instructions which have certain similar requirements, and then you try to come up with some instruction formats so that you can encode this the information correctly. Now, how many bits do I need to encode all this information? In this example, I said I am assuming we have a 32 bit word length, and then we came up with this kind of a encoding. Okay. Now, when you have other factors to be considered, let us look at what we actually need to think about. So, let us say for instance, what happens if I want to specify a memory operand using the absolute addressing mode. Previous example, we had assumed that the operands are in registers, right, which is why we said 4 plus 3, 7 bits are sufficient to specify the source and destination operand. But what if this source and destination operands were actually specified using absolute addressing mode? Therefore, we need to specify a complete memory operand, right, using this absolute addressing mode. Now, when I need to specify a complete memory address, right, for instance, if I have move R2 comma lock like this, suppose we had only 14 bits are available for specifying the location. Would that be sufficient? Most probably not, right, because the location here will have to specify the memory address, and depending on total number of memory locations we have, the number of bits required to specify unique address will be different. So, if I had for instance 1 megabyte of memory, so I would require 20 bits to specify the memory location. So, it is not enough if I have just 14 bits available in my addressing mode. Okay. So, what do you do in that case? In that case, what we do is, instead of specifying the entire instruction in just one word, we would use 2 words to specify it. So, for instance, you may have something like this. So, we just now said we can have opcode, source, destination, other information, plus we will be using one more word here where the memory address or some other immediate operand, whatever, that can be specified. Okay. So, if you had for instance, so now in this case for instance, if this whole thing was a 32 bit word, so I have provision now in this instruction format to specify a 32 bit address, which means up to 2 to the power of 32, which is 4 gigabyte of memory locations can be specified here. Okay. So, this would give me a 2 word instruction. Now, remember, one instruction does not get over in one word, but I will have to use 2 words for the instruction in this case. Now, next question is, what if 2 different operands, right, can be specified using the absolute addressing mode? Now, in this previous example, we only had one instruction specified using the immediate addressing mode. So, maybe it was the source or the destination which was specified using this. Now, what if both the source and destination had to be specified using the absolute addressing mode? So, now you can see that it is not sufficient if I have just one more 32 bit word to specify this. I will now require 2 additional words, right. So, if I have move lock 1 comma lock 2, which means this is a memory location being specified, this is another memory location being specified, complete addresses have to be specified. So, the solution now would be to use 2 additional words. Okay. So, what will happen now? Your instruction now will become a 3 word instruction. So, what basically happens when you start adding these different kinds of addressing modes and start looking at how to take care of all these different variations, is that you might end up with instructions of variable length. When you say instructions of variable length, it means certain instructions would be taking up only one word, certain instructions would take up 2 words, and certain other instructions may take up 3 words or even more than that, depending on what kind of encoding we follow. Okay. So, what happens because of this is we end up in what is called as complex instructions, right? And so these complex instructions normally they closely resemble high level programming languages, and when we have such kind of complex instruction set in our instruction set design, it is referred to as a complex instruction set computer or a CISC architecture. Okay. This is a term that we would have heard about earlier, we also referred to this earlier. So, we come up with a complex instruction set computer when you have provision for these kind of different types of addressing modes, all possible combinations of addressing modes, and have all these variable length instructions. The problem with these kind of CISC instructions is that it becomes difficult to handle it with respect to decoding the instructions and so on. It becomes more complex basically, not difficult, it is actually becoming more complex. The advantage of course is that these complex instruction sets, their power is much more, right, because a single instruction could be doing a lot of operations. So, the instructions would closely resemble a high level language, in that sense it can be a much more powerful instruction, but it is complex. Okay. And normally to understand how the encoding gets done, it is easier to look at it from the point of view of a simple instruction set architecture, where we go in for, instead of a complex instruction set computer, we look at a reduced instruction set computer. Okay. So, now what we will do therefore is try to take a look at example of a RISC architecture and try to understand what happens. So, what we do in this case when we are trying to go in for a RISC based architecture is that we try to restrict the different types of addressing modes that are possible. So, you can see that when we restrict the addressing modes itself, it is the number of combinations that we have to look at becomes less, and when the number of combinations becomes less, we can arrive at some simpler formats. Okay. That is the idea that is normally used in these RISC architectures. So, for instance, if I say for instance that I will insist that all instructions must fit into a single 32-bit word, it is obviously it is not possible to provide a 32-bit address or a 32-bit immediate operand within the instruction. So, what do I do then? That means, does it mean that I can't have an immediate addressing mode, or I cannot have an absolute addressing mode? That will be the question that comes in, right. So, what we do in that case is we will provide these addressing modes with some restrictions. For instance, you may have an immediate operand, but you may not provide a 32-bit immediate operand, you may only provide for a 16-bit immediate operand. So, those are certain compromises that we will do. Okay. Similarly, it may not be possible to provide a 32-bit address directly, but you may have some kind of a base plus offset combination which may give rise to a 32-bit address. So, we need to work at these small changes to the basic structure to arrive at the right set of addressing modes, so that all instructions can fit say within a 32-bit word. So, why this restriction that all instructions must fit within a 32-bit word? Basically, it makes it very simple to do the decoding and makes it simple to handle the entire set of instructions in an efficient manner within the processor. So, what we therefore do normally in these kind of architectures is that we go for more for a register based architecture. So, where we say you will have a highly functional instruction set which makes extensive use of the processor registers. Okay. So, you will have instructions which basically work more on the registers and less on directly on the memory locations. So, typically we go in for what is called as a load store architecture, wherein only loads and stores will be accessing memory locations, and all the others would act only on the registers. So, for instance, I would have add R1 comma R2, this is an agreed instruction. Add location comma R2, this will not be agreed. Okay. So, this is no. Similarly, add R3 comma R2, this is an indirect addressing mode, this is specified, this is yes. Okay. So, these are the types of things that you could do if you want to restrict the total number of instruction to fit within just some 32-bit words. Okay. So, this is how we basically deal with reduced instruction set computers. So, we will take a break now and come and take a look at an example of a RISC architecture. Welcome back after the break. So, we were just looking at how to encode an instruction, and we talked about a complex instruction computer where the encoding can be a more complex mechanism, and a reduced instruction computer where we normally try to have simple encoding mechanisms. So, an example of this RISC architecture that we will look at now in this half of the session today is based on the MIPS architecture. The MIPS processor It's a very good example of the reduced instruction set set computer. This was initially proposed at Stanford University and it was commercialized later by MIPS Technologies. The importance of this architecture basically is that it is used in many products and it is typical of many modern ISAs. Okay, it is used in applications in consumer electronics, network, storage equipment, cameras, printers and so on, and many of the RISC architectures are very similar to this. So, this is a good example of a RISC architecture. So, we will take a look at this. What we have in the MIPS architecture is that arithmetic instructions basically use register operands. Okay, we said this is one of the characteristics normally of a RISC architecture, and it has a large register file. It has 32 registers, each register is 32 bits in length. Okay, so we say it has a 32 cross 32 bit register file. Now, we know that a group of registers is referred to as a register file. And so, this is the one that is used for frequently accessed data, and these registers are typically numbered as 0 to 31. Okay, and the 32 bit data is called a word. And the assembler names for these registers, they are this slightly not very intuitive naming of the registers. The registers are identified as $T0, $T1 etc., $T9 which are used for storing temporary values, and then we have $S0, $S1 etc. as the registers which are used for storing saved variables. So, we will see how that gets used with a simple example here. Suppose you had a C code like this, f is equal to g plus h minus I plus j. Okay. So, f, g, h, I, j, all these are variables which will be stored in registers $S0, S1, S2, S3 and S4. Okay. So, the compiled MIPS code, the MIPS assembly instruction for this instruction would be, I need to add this number and then subtract this from here, right. So, add $S1, $S2, store it in $T0. Okay. So, S1 and S2, these two values G and H are added, stored in T0. Similarly, I and J which are in S3 and S4 are added, stored in T1. These are two temporary values which are used, and now T1 is subtracted from T0 and the value is stored in S0 which corresponds to F. Okay. So, subtract S0, T0, T1. So, this is what a corresponding MIPS code for this kind of a C code would look like, just to give you a feel of how the assembly will look for a given high level language using this MIPS architecture. Okay. So, that is with respect to the register operands. Now, if you are looking at memory operands, handling of memory operands within the MIPS architecture, a main memory is used for array structures, dynamic data and so on. So, we basically have two operations, load and store. Load values from memory into registers and store result from register to memory. Okay. And the memory here is treated as a byte addressed memory. So, each address identifies an 8 bit value and the words are all aligned in memory. So, address must be a multiple of 4. Okay. This is another alignment requirement that is there in the MIPS architecture. And MIPS is big endian. Remember, we have talked about big endian and little endian formats. Big endian means that the most significant byte will be at the least address of a word. And remember, in little endian it means least significant byte would be at the least address. So, this is MIPS uses a big endian format. So, now again looking at a C code example for how memory operands would be used. So, suppose we had a C code like this, G equal to H plus A of 8. Now, so let us say G is in $S1, H is in S2, right, and the base address of A is in S3. So, what will be the corresponding code for this? So, we have let us say a load word instruction LW T0, 32 of S3. Remember, this is a memory address that needs to be added, right, memory operand that needs to be accessed. So, memory operands can be accessed only using a load instruction. So, we will load this value which is available at A of 8, okay, using an indexed addressing mode. So, index 8 requires an offset of 32 assuming we are using 4 bytes per word. Okay. So, you add 32 to the base address which is there in S3, base address of A is in S3. So, S3 plus 32, right, that would be the memory allocation specified by this. So, you have the base and you have the offset specified here. So, that is the address specified for loading into the register T1 which is a temporary register. Then now you can add T0 and now this T0 is added to S2 which has the value H. So, and that value is stored in S1 which corresponds to G. So, you will have a load word and an add instruction in order to accomplish the statement that we have here. If you also wanted to store this instruction, let us say in another memory location, so A of 12 equal to H plus A of 8. Now, look at what will happen here. The first two instructions are the same which have to do this function of H plus A8, but what is the third operation is that I need to store the value not in a register now, but I need to store the value in this memory location. So, now what will happen here is I will load the word as I did in the previous case and I will do the addition, but store the added value in another temporary register itself, T0 itself let us say, and now the store will store this temporary value which is register result which is there in the temporary register T0 into the memory location A of 12. Now, A of 12 how do I point to? I know that my S3 has the base of the array A, and now I need to look at the 12th element. So, 12th element will be would be available at an offset of 12 into 4, 48 bytes. So, it becomes now the offset now becomes 48 of $S3. So, you can also store the word. So, this is how memory operands would be accessed, right. So, if you look at these, you will get a kind of idea of how you are trying to manage with registers in most places, okay, and specify only some offset information and so on. Now, if you are dealing with immediate operands, okay, how does immediate operand, how is immediate operand dealt with in this MIPS architecture? So, the constant data is being specified in instruction like this. So, you have for instance add I normally indicates it is an immediate mode, S3 comma S3 comma 4. So, the value 4 is now specified over here. There is normally no subtract immediate instruction which is provided in MIPS, because the same thing can be achieved using a negative constant. So, you can have for instance instead of doing subtract 1, you could say add I S1 comma minus 1. So, this is something that is used. So, the design principle that is used here is that you make the common case fast. So, small constants are common, okay, and the immediate operand avoids a load instruction in that case, which is why you provide for an immediate operand, but you do not worry about having large constants here, okay. So, the value that you can have here specified as a constant normally is restricted to a small number, you can't have very large numbers. Another important interesting aspect of the MIPS architecture is that you have the a special register 0, which is used to store the value 0, okay. So, a constant 0 is stored in the register 0, okay, $0 for instance, it has this constant value 0 and it cannot be overwritten. Now, what is the purpose of having a 0 register like this? You will see that many times we will be doing initializations where we start with some value 0. So, instead of having to explicitly load from a memory location or set a memory location to 0, you can just use this register because it already has a value of 0 that is stored in it. So, for instance, if I want to do something like this, move between registers. So, add T2 comma S1 comma 0 if I want to. So, what does this do? I accomplish basically a move instruction using this, because S1 plus 0 will be stored in T2. So, what is the effect of that? S1 plus 0 is S1 itself. So, same value will be stored in this register. So, you can do movement also using these kind of addition instructions and so on. So, a lot of interesting uses for this kind of a constant 0 kind of register. Now, coming to the addressing modes that are specified, that are supported in the MIPS architecture. So, as we saw, you have support for immediate addressing. So, you will have an operand, 2 registers specified which are called as RS and RT, and an immediate value, okay. This is something which we have. Then you have register addressing, so where you can have 3 operands, all 3 operands are specified as registers RS, RT, RD, okay. And then there may be some other additional functions which are specified. So, this is support for register addressing. Then we can have base addressing, where you will specify RS, RT and some address information. So, here this address is added to some register value, right, and that gives you the location that we need to use for accessing a memory location. So, remember this is our base addressing, the base is in some other register and the offset is specified in this register. And this register, again, which register has to be used could be specified by one of these registers RS or RT which is specified here. So, we have support for immediate addressing, register addressing, some form of an indexed addressing which is base addressing, and then we have support for PC relative addressing, right. So, where again you have an address value specified here, this value will be added to the PC value in order to access the memory location. There is also one more addressing mode which is specified, which is called as pseudo direct addressing, wherein you will have an opcode followed by complete address information which can be stored directly into which will be of course again taken with respect to the PC, and that operation will be used, okay, you can use a different kind of an operation over here to attain the effective address. Okay. So, with these different addressing modes, you can see that though we have looked at large number of addressing modes, the number of addressing modes supported here are restricted, but with this you can pretty much achieve all the different operations that we have talked about. And what is the advantage of doing restricting these kind of addressing mode is that the advantage is that the representation can be done now with just fixed instruction words of 32 bits. Okay. So, let us look at how that is done. Okay. So, this representing these instructions. So, the register numbers that are used, we said we use 32 addresses, right. So, T0 to T7 are registers 8 to 15, T8 to T9 are registers 24, 25, S0 to S7 are registers 16 to 23. So, these are how the registers get mapped, and all the instructions are coded as 32-bit instruction words. So, let us look at the different formats that are used here. So, we have actually there are 3 different formats that MIPS uses, an R format, an I format and a J format. So, in the R format what we do is, this is the way the R format is specified. You will have an opcode which uses 6 bits and then an RS register field, RS 5 bits for that, RT 5 bits for that, RD 5 bits for that. So, you have 2 source operands and RD which is the destination register, okay, destination operand, and then there is a SHAMT field which is basically shift amount, okay, and then there is a function field which is again 6 bits which can be used to extend the opcode. So, just pay a little bit of attention to the number of bits used over here. If you look at the opcode field, it is using 6 bits, which means I can have 2 to the power of 6, 64 different opcodes. So, 64 different instructions can be specified, but if I needed something more, some variation that I need to specify within each type of instruction, I can use this function bits to specify that. Okay, so, I have another 2 power 6 different values available for doing that. Another thing to note here is, we use 5 bits for the registers because we have altogether 32 different registers. So, we need 5 bits to specify that. So, with these R format instructions, most of the arithmetic instructions can be handled. Okay. So, RS and RT give you the first source register and second source register, and RD gives you the destination register number. This is an example of an R format instruction, add T0, S1, S2. So, you can see that you will be specifying the opcode, you specify which register is being specified here, and then the destination registers. The shift amount is 0 for an add instruction, and function is specified here as add. So, you can see how this will get coded basically. The binary values for each of these values is specified here, giving you the complete instruction. Okay, this is what an R format will be used with. The I format instruction would look like this. This is basically used for immediate and load and store instructions. So, you have only 2 registers specified here and 16 bits are available for specifying constants or addresses. Okay. So, the constant can, it is a signed number, it can go from minus 2 power 15 to plus 2 to the power of 15 minus 1, and the address is generated by adding the offset to the base address in RS. So, RS plus this offset, that will be the effective address that is calculated in the I format instruction. Conditional instructions are handled by the J format instructions. Okay, you have branch instructions handled by this kind of similar I format instruction using PC relative addressing. So, when we say PC relative addressing, remember the PC plus the offset has to be added. So, the constant again here is used to specify the offset, which is added to the PC. Okay. So, this is what is used for branching, and jump and other instructions, they use a J format instruction where you have just 6 bits for the opcode and the rest of the 16 bits here specifying the address. So, this 16 bits multiplied by a value of 4 gives you the target address. Okay. So, these are the different addressing modes which are supported in the MIPS architecture. So, to summarize, so what we have looked at is, we have looked at size of various fields, how the size of various fields are calculated for an instruction encoding, and we have looked at one ISA example which is the MIPS architecture. It is an example of a RISC architecture. It uses fixed instruction sizes and limited formats. Just we saw that there are only 3 formats that are used to give our required complete set of instructions and addressing modes. Okay. So, few questions to review what we have been looking at today. Question number 1, what are the important factors to consider in encoding instructions? Question number 2, what are the addressing modes provided in MIPS? Question number 3, what are the instruction formats in MIPS? Question number 4, what is the purpose of register 0 in MIPS? Thank you.